Hello everyone, it's June the 2nd. Alright, so today's goal is finish the challenge, and I want to continue on the path from yesterday. So yesterday we learned a very smart leverage of Python's bisect. So we can use bisect to do any binary search algorithm in Python 3.10 because bisect adds a key parameter to it, which is just telling bisect how to make a comparison, how to transform the elements in the original list in order to compare to your target. And because of that, we can set a target to a Boolean value, and then we can use this key to do any types of transformation of the list, the values in the list, which makes bisect left and bisect right become legitimate binary search algorithm that can suit for any needs, and is guaranteed to be correct. So this is absolutely good, fine, very good, fine. So what I'm trying to do today is, after solving the challenge, I'm going to find one binary search problem and then just try to see if I can solve it using that thing. I already did it yesterday actually with this square root, and then you can see here it freaking works. So I'm going to just try something else and see how it goes. Alright, so this is today's challenge. Range sum. Ooh, I remember this. I remember this thing. Okay, given a 2D matrix, handle multiple queries of the following type. Calculate the sum of the elements of a matrix inside a rectangle defined by its upper left corner and lower right corner. Implement num matrix. Initialize the object with the integer matrix. Sum region returns the sum of the elements of matrix inside the rectangle defined by its upper left corner and the lower right corner. If I remember correctly, it is, let's see, so 2, 1, 4, 3, so 2, 1, 0, 1, 2, 2, 1, 4, 3 is going to be this one, so I just add these together, right? 3, 6, 8, okay, so it's a range sum. That's the topic, at least for this week, I guess, a range sum. So this, I think it's a 2D, right? No, it's not the other problem. It's not the other problem that I had in mind. I think this is just a basic 2D prefix sum. All right, so we do prefix sum on this, and then we do this, and eventually every value is the sum of the rectangle starting from the top left until this one. So if we add, so we have prefix sum on each row, and then for each column we just add a 1 above it. We add a 1 above it, and this one equals this plus this. This one equals this plus this. So this plus this equals this full thing. So each one is a sum of the entire thing that we're given here, right? So what we do, we find this value, which would give us the sum of this entire giant thing, and then we're going to minus. So we're going to minus this value, right? So minus this, and then minus this value, right? And then because these two get minus twice, so we find this, and then we plus this, then it'll be here. Now, the difficult part of this is edge cases. Because like if it's above, then that's actually 0, so we don't minus this. Hold on, So like if we go here, right, we have this, that entire thing, and then usually we shall minus what? Or minus this, right? So we shall minus the one above, but we don't have them above, so it's a minus 0, and then we can minus this one, and because of this one will be 0. Maybe it's fine. Okay, let's just do this. All right, so the self.mat equals matrix, okay, and then self.prep mat, self.prep. All right, so don't try anything. So we can say for row in self.mat, I in range 1 to, well, actually, let's do this, self.m equals len self.mat. Hold on. They guaranteed it to be 1, yes. And then this m self.mat 0, okay. Now in prep, and then this will be self.n, and because of this is actually so this one is going to be j, okay. Say self.mat. Ooh, I don't say self.mat. Row j plus equal to row j minus 1. Yeah, this one equals plus equal to the one that had a bit before me. So that's, and then we do it again. Just do that here for j in range. Oh, hold on. Yes, so I'm going to say so I this in enumerate, right? And then we say if I is larger than 0, and then this should be self.n, because we should start from the first one for j. We say row j. So we do that, and then we add to the top. So we say row j. Yeah, so we need to do this first, and then add to the top. Row j plus equal to matrix, no, self.mat I minus 1 j. So that's prep. Okay. So after we do prep, in some region, you have this value, right? And then I'm going to say we call it ABC, right? So A shall equal to so row 1, column 1, row 2, column 2. So we call it row 1 minus 1, right? Row 1 minus 1 and row 2. B equal to, B is this one. We call it row 2 and, right? B is row 2 and column 1 minus 1. And C is going to be row 1 minus 1, column 1 minus 1. All right. And then what do we say? We say actually, I don't like this one. Hold on, I'm gonna do it again. We just say if row 1 minus 1, that row 1 minus 1 is larger or equal to 0, A shall equal to actually we can do it this way. A equal to self.mat row 1 minus 1 row 2 if this, right, else 0. B equal to self.mat row 2 column 1 minus 1 if column 1 minus 1 larger equal to 0, else 0. C equal to self.mat row 1 minus 1 column 1 minus 1 row and column if row 1 minus 1 larger equal to 0 and column 1 minus 1 larger equal to 0, else 0. Return self.mat 2 column 2 minus A minus B plus C. All right, let's see. Oh, actually, we have to test this way. What? Well, one example. Oopsie doozy. The first one got wrong. Oh, a couple wrong. How? Let's see, maybe it's the prep. I don't see a problem. Well, we can just print it. Then we'll know the problem. All right, let's see. 3, 3, 4, 8, 10. 8 is 14. That's correct. 22. Ooh, this one's not right. No, this one is right. This is 8. That's 14. 18. So the first one, right, was 38, which is this entire thing. I'm going to minus 14, give me 24, and minus, that's a 0, plus 8. Yeah? How did I not get it right? I don't know. Nope. Oh, column. Typo. There we go. $700. Here's 700 days. All right, let's just see. What else do we do? I think it's a pretty standard solution. What else can we do? I don't know. Yeah, we do have a. All right, this is column 2. This is a pretty standard solution of 2D prefix sum. OMN. $11 test cases. Yeah. Oh. I see. 11 pi. I see. How many test cases this time? 24. Previous is 11. Okay, so that will be it. And like I said, I'm not gonna do any of these. Oh, this is just the very, very good solution from yesterday. Okay, what we're gonna do, so I wanna keep trying, so I think it's binary search. Where's binary search? Here we go, binary search. So that's a real question that we haven't done before. Can I do first bad version? We can try this. Hard problem. Yeah, I don't think I'm in the mood for hard problem today. Another easy one. I don't know. I want to do a medium one. Friends of appropriate ages. Okay, so let's just try this one. So basically, I want to try to solve these problems so that I can have enough material to write the article. I want to like expand this into an article, like how my thought process behind it. It won't be too difficult to write, but I want some good resources for this. All right, so first bad version. You're a product manager and currently leading a team to develop a new product. Unfortunately, the latest version fails the QA since each version is developed based on the previous version. All the versions are after a bad version also bad. Suppose you have n versions and you want to find out the first bad one, which causes all the following ones to be bad. You're given API is bad version, which returns whether the version is bad. Implement a function to find the first bad version. Should minimize the this is n equals 5. Bad equals wait. What's bad? It didn't explain what bad is. Oh, you're only given n. You're only given n. What the hell is this then? All right, so yeah, with binary search, let's write it out. It'll be fun. What is this? 278. All right, so right. So binary search. We want to search this and this, the first one that. So if it's good, right? So I'm going to do some notes. If it's so first of all, we have to remind ourselves the left, right? So bisect left, it's key smaller than the target. We say low equals mid plus 1. Right? If else high equals mid. That's how it goes. So in our case, we basically ask, when do we do low equals mid equals plus 1? So we do mid plus 1 if we have a case that returns good, right? If the version is good, then we need to keep search. If the version is bad, then so version is good. So we want key smaller to x return true. If it's good, right, we want this one return true. And x is true. So for this return true, the key must be false, right? So if it's a good version, must return key equals false. Okay, that's the condition. So what we want is bisect left range, and so 1 to n plus 1, that's the range. That should be true. And key equals lambda v. So we can call a function called is bad version, right? Is bad version. 3 is false. So is bad version. So we're gonna call this function. And we said if it's a good version, we want to return to false. So we can just directly call it, because is bad version, if it's good, will return false. So this one will, what will it return? It will return the first version that is bad, right? It will return the first version that is bad, but we want to return the first bad version, which, if you think about it, it's like bisect left. Yeah, we can do this. So we return this one. Okay, let's see. Ooh, the logic. Think again. So we say if it's a good version, low equals mid plus 1. So in the first case, we have 1, 2, 3, 4, 5. 4 is bad. The first 3 are good. Right? So the first thing we check is 3. Right? And then 3 is become false. And false smaller than return true. So low equals mid. So low now becomes 4. Oh, wait. This one returns bisect returns the index. Bisect returns the index. So if it returns index, why don't we just go this? Right? There we go. Yeah. And I think if we change this to bisect right. So bisect right is if x is smaller than key, returns, so high equals mid, else low equals mid plus 1. Right, so we want x smaller than key. Well, x smaller than key evaluates to false when it's good. And then this is false, so when it's good, right? Which means we want key evaluates to false when it's good. So it should be the same. If we run this, yeah. So this is use bisect right. Okay. This is like another example, but it's slightly different. So, okay. Yeah, I have to go this way. All right. So I have 2 examples, right? 2 examples, but we cannot start from 1 because remember, it only returns. Yeah, this is actually a good example because it shows us, right? It shows us it has to be. We have to keep in mind that it returns in an index. So how long have I been doing this? 29 minutes. Yeah, let's roll a little bit longer. First friends. Let's do this. First friends. Not first friend, just friends. So it says friends of appropriate age. There are n person on a social media website. You're given integer ages, where ages I is the age of the ith person. A person X will not send a friend request to a person Y if any of the following conditions true. If age y is this, if age y is that, if age y is this, or an age y is larger than 100 and age x is smaller than 100. Otherwise, x will send a request. If x sends a request to y, y will not necessarily send a request to x. Also, a person will not send a friend request to himself. Total number of friend requests made. Will not send if any of the following is true. Okay. So if it's 16 and 16, they send to each other. So for 16, I have 17 and 18. So I'm going to check this. If age y is, so 16 cannot send to 17 or 18. Okay? So 17 cannot send to 18, but 17 might be able to send to 16. Then I need to check. 0.5 times this plus 7. So 17 and a half, what was that, 8.5. 8.5 plus 7 is 15.5. So I can, and this one good because age y is larger than this. Age y is smaller or equal to age y. So 17 is sent to 16. 18 is sent to 17, but 18 cannot send to 16 because 18 divided by 2 is 9 plus 7 is 16, so I only have 2. Okay. We want to find out the total number of friend requests. So yeah, we sorted, right? And after we sort, we know the smaller one cannot send to the bigger one because of the restriction. And so we say, basically, given a value, we want to find out how many people I can send requests to. So my age is 120, right? My age is 120. And I want to find out because the people I can send to, they must have a smaller age, which is just to my left. That one is solved. Smaller or equal to me, right? It's solved. And they have to be larger. So the age y must be larger than age x divided by 2 plus 7. So basically this is something we can binary search. Okay. For binary search we will get to, oh, this one's directly bisect. This one's directly bisect. We don't even have to do any transformation because that's just the age. We're given this age and then we bisect. So the age has to be larger than this. So it's equal, it doesn't work. So we will go bisect right. Okay. And then last one, if my age is larger than 100. No, if my age is smaller than 100, then the person's age cannot larger be. Yeah. If my age is smaller than 100 and age y is larger than, this is the same as this one. Which means if my age is larger than, then it's fine, right? Based on what this one says. Yeah, if x age is smaller than 100, then x is definitely smaller than y. So this condition is contained inside this condition, so we don't even have to consider this condition. So, and then this condition is so we only have one condition actually, and we just need to binary search this. Okay. Yeah, but this one is just a straightforward binary search. Huh. Well, I guess, what are you doing, man? I guess 2 examples is good enough. I don't know. Yeah, it's not going to be a long article. It's just going to be a short article and then describing my discovery, citing the people that I got it from, and that shall be it. It's going to be bisect, right? Right. Age is of sort. Right, and for I range, len ages -1. I can't just do 0 because the last one I have 0 people I can send. Ooh, hold on. Hold on, I just realized the same thing. If it's the same, then the person, if we have, let's say, a bunch of people, we have the same age, and then they can send. Okay, we have a better idea. So we need to from collections. Port counter. We need to use counter. Counter equals counter ages and sorted ages equals sorted counter. Okay, and then we can actually go reverse, right? Reverse equals true. We still need I though. Yep, no. But anyway, so this one will be sorted ages. Yeah, and then it's sorted ages, we don't have to include if it's sorted ages, we don't have to include the first one because that one doesn't have. Okay, so in this case, temp equals counter, right? Sorted ages. Let's just call A equals sorted ages I, okay, and counter A -1 because it's the same age, right? If you're the same age, you can send to all the other people of the same age. So you have the temp, which is just not you, you can send to everybody else. And then we're gonna do bisect, right? So we're gonna say bisect right sorted ages, the current age, and then we have a low and a high. So I think we just set high shall equal to actually I don't even need a high, and it's not A. Come on, it's A divided by 2 plus 7, right? Current age divided by 2 plus 7, so that gives me thing. So if it's smaller than this value, it doesn't work. So it has to be larger than this. So a binary search for this value. Okay, binary search for this value. And if it's bisect right, so if it's the same, it bias towards that one. So this index, right, this index give me is the correct index, and I need to find out how many people are in these range. I just realized this might not be. No, we should not use, we should still use counter, but we shouldn't use sorted ages. We shouldn't use sorted ages. We should just say ages.sort. Yeah, because otherwise we have to go inside counter to find how many there are. So just ages. And then so A is this. This is needed, right? Counter A was needed. But after that, the bisect shall just be ages, right? So now we have the entire ages array, and now we find a value. That's actually the minimum value, and we do bisect, and then we do bisect right. Okay, so all the way here. So now the total number is from this index to my index. Holy guacamole, to my index. My index. It cannot be my index. I need the bisect right and the bisect left. Because I can't. Because out of it was me, I'll be counting the repeats. Oh, you gotta be kidding me. You gotta be kidding me. 2 rounds of bisect. But now that if we do 2 rounds of bisect, oh my god. We have to do 2 rounds of bisect. If we don't do that, we have to iterate through. That's definitely not the case. So if we do that, because we need to find the front edge and the trailing edge of the age I can now do, and the front edge of my current age of my repeats. Those are the ages in between that I can be friends with. And then I add, yeah, I think unfortunately, at least that's how I see this problem. We have the bisect right and the bisect left. So we have a index 1 equals this, right? And index 2 we go to bisect left ages and put my current age into it. So index 1 we hit there, index 2 and we hit here, right? And then it's never going to be the first one. And bisect right is going to be The bisect left is not going to be a problem. It's always going to work, because the worst case. Okay, let's think about it this way. Bisect right. We're looking for something that's smaller, right? So it's always going to find 0, right? It's going to be find 0 if, let's say, it just doesn't exist, right? It's just going to be 0, which is, you know, let's say totally fine. Yeah. So bisect left, bisect right is fine. Bisect left, as I want to find out my current age. All the way, I want to push to the left. Okay. I push over to the left. It'll be 0 as well. So the total count should be index 2 minus index 1 plus 1. Right? But there is an issue with bisect left, because bisect left and then bisect right, then that's 1, right? But if it filled the entire thing, then bisect left, ages is what? 1, so I add a 0 to ages. Yep. We append a 0 to ages, so we always have something small. In this case, then bisect right is always going to be correct, because we always have something small, so we always can find something. Bisect right is going to, left is going to be correct, because we always have something small. So in that case, bisect right, small value, I'm going to find this one, right? Because it's in between these, it's larger than, so I'll find this one. Bisect left and find this one. And 0 minus 1 plus 1 is 0, okay. So, blah blah, temp plus equal to index 2 minus index 1 plus 1. Right. Once we're done, res plus equal to temp. So if that's the case, why don't we start with res? Right? Why don't we start with res plus equal to this, and then res plus equal to this, then we can save a line. Right? And now return res. Actually, I feel this is not that simple. All right, so we have a few test cases. That is a 2. That is a 2. And that is a 3. Ages. Number of friend requests. Ages. Ooh, that was terrible. How is it 4? Let's see what went wrong. Okay, so ages is 16, right? That shall be +1, and then bisect. Yeah, we'll just print index 1, index 2. So they call it twice. Oh, of course, because I call it twice. There we go. We should only call it once. All right, we have problems still. This one's right. This one. Yeah, we don't include 16. So we have 17 and 18. Right, we'll do 17 and 18. Okay, print index 1, or we print A, index 1, and index 2. So 18, index 1. We're looking at 16. Bisect right 16, so I should put in here 0, 1, 2. That's 2, that's correct. And this one, bisect left, put in 0, 1. Shouldn't that's 2 as well? Oh, I should be -1. That should be -1. But how about this? So hold up. So this one's still gonna work? Yeah, this one's not gonna work. Why? Because we're trying to find, and then this one will return 0, right? And then 0 minus 1 plus 1 is 1. And this one we didn't really check. I see. So why do you not allow it to go? Yeah, now I think I can allow it to go. Earlier it was just like we have 2 errors, but now I think it's actually fine. Yeah, we can let it go. There we go. Yes, we absolutely can. Yep. This is shaping up. Oopsie doozy. Yeah, let's just go. Oopsie doozy. Binary search is always like this. Output 2, expected 3. Okay, so we need to print some stuff. First, we're going to print ages. Now we're going to print A, index 1 and index 2. but not all of you. Okay. The problem is with 5. Index 1 is 2. Oh, shoot. Yeah, it has to be, man. We're going to say if age is larger than. We can actually calculate it. 14. All right. If it's 14, then if it's 14, then the minimum age is 14. It has to be larger than 14, and I cannot do. So if it's going to be, so are you saying if you're younger than 14, then you cannot send any requests? That's true. So it has to be, if A is larger than 14, you can't even send to yourself. So if A is larger than 14, then we do all this. Yep. I'll have another print. All right. Again. Yep. So a few edge cases. One is that one is to handle repeated ages. Now this solution uses a counter to obtain the number of repeats. If a person is old enough, she can send friend request to anyone of the same age. Another edge case is the requirement that the target must be older than a divided by 2. A divided by 2 plus 7. This actually gives us a minimum age that that is allowed to send friend request. 14 plus 1 equals 15. Thus, anyone younger or equal to 14 years old cannot send friend request. So in this case, if a is smaller or equal to 14, then we just simply break. And we don't need this. We can just simply do this, and it will pass. So when log n. Let's see. Maybe this one's faster because we don't have to go all the way down. This one's correct. Let's see if we can get a little faster because we'll break out earlier. It's okay. All right. 89 test cases. 683. 683. 28%. Okay, so we've done this. Oh, it didn't do binary search. That's correct. Wow, it is very straightforward. It doesn't have to be binary search. Let's do this. That'll be fun. So this one will be solution 2. No binary search. Courtesy of Lee 215. Him again. It's always him, man. It's always him. Alright, so we still need a counter, which is fine, ages. And then what? And then we just iterate through these, right? We iterate through this, iterate through this, and then just compare. We can sort it again, actually. But we can avoid the sorting. Yeah, we can avoid the sorting. Just do that. We just say for I in range, say len counter. Okay. And for j in range, I plus 1. Oh, I can do I to len counter. Right. Okay, so we have 3 conditions. We say because I is the sender, J is the receiver, right? So I is the sender, J is the receiver when they check if J makes sense. So we say if, what are the conditions? I forgot. The condition is if age y, so if ages j is larger than ages I divided by 2 plus 7, if this and ages j is larger than this and ages j is smaller, equal to ages I, right? And rest plus equal to counter, because I have ages I times, because everyone can send a request to everybody else, ages j. Okay, so blah blah blah, and if they're the same, oh, I also have to do the same. So what can I do here? Right, if ages if I is not equal to j, right? If I is equal to j, then it's going to be counter ages I times counter ages I minus 1. Okay. Now what? Now return rest. That was terrible. Oh, do you still have to sort it? Otherwise, everyone has to go through the entire thing. No, let's now sort it. So in this one, it's just going to be there. We go. No binary search. Eh? What the heck? think I double count some stuff. How? Oh, it's not ages. I don't know what I was thinking. Oh man. For A encounter. B encounter. Alright, so all the ages, all this is B. All this is A. I have a J. This will be A, and this is B. There we go. Unbelievable. That was such an oversight. It's a lot faster than binary search. This is O n squared, but it is much faster than binary search. Because the size of the counter is very small, at most 1 in 20. Alright, that will be it. So we didn't really have, this is not really a binary search problem, but it's okay. It's okay. We have some resources that we can use to write the article. We'll do that. Alright, that will be it for today. I'll see you guys tomorrow. Adios.